Okay. Now, we are in unfolding chapter, but then we will do little bit of different things now, things which will initially appear to be somewhat different. See, so long we have been drawing lines like this, going into a node U, then like this V, maybe some delay W. Here I say xn. This xn actually is a line, but in digital hardware it is a bus. It may have 16 bits in parallel or 32 bits in parallel. So, it is a bus, there may be parallel lines in general. So, it is a 16 bit word, all the 16 bits will come parallelly. Okay. So, one word means the whole data xn, next is another word, next is another word, they come through the bus. This kind of structures where the bits are parallel, okay, they are called bit parallel or word serial structure. Okay. Word serial and bit parallel structures. That is, all the bits, the 16 bits, they are coming entering the system parallelly for every word. Word is coming cycle after cycle, nth cycle, one set of 16 bits go in, n plus 1 cycle, another set of 16 bits go in. So, bits are parallel or whole word is serial. Okay, this is the thing we have been assuming, that is why instead of showing all the lines, bus lines parallelly, we just show one line, but it is understood. I am basically talking about a bus. So, this is called word serial structure. To continue, suppose I have got a digital system. It takes two input, A data and B data. A data may be like this, six lines. So, this is A. So, LSB A0, okay, you can write as a function of n, is the nth clock, nth data clock. I have got input data an, whose 6-bit representation like this, A0n, which is a binary bit, either 1 or 0, then A1n, A2n, A3n, A4n, A5n. So, A0 to A5 at the nth clock they go in. So, all the 6 bits, because data here I am saying to be 6 bit. So, all the 6 bits of the data they are going parallelly. So, bit parallel or word serial structure, I mean for A. Similarly, it can take another one B as an example only. This is Bn, so it may have B0n, B1n, B2n, okay, and output could be the nth clock, output will be again its LSB, least significant bit will be this. All right. So, this is a perfect bit parallel word serial system. There is one extreme opposite of it called bit serial. Actually, in this digital system, whatever it is doing, maybe it will take a bit of A0, bit of A0n, B0n, it will do a processing on that, give you C0. Same processing it will do on A1 and B1, it will give you C1. Same processing it will do on A2 and B3. I will show an example, A2 and B2. So, there will be various processors just parallel, okay, one giving C0, one giving C1, one giving output C2, one giving output C3 parallel. And parallel, that is why it will take more power, okay, more hardware. all right, but it is fast. That is, I mean, I am not wasting any cycle. There is another extreme of it. When I go to that, this will be this it will be further clearer. This is called bit serial. In bit serial, what is happening? If your nth clock of the input, here this over the entire period in the first diagram, I had A0n either binary 1 or binary 0 standing in this line for this entire period. Simultaneously, A1n, which is either binary 1 or binary 0, was standing over this entire period on this line. A2n, which is again a binary bit either 1 or 0, was standing on this line for this entire period, which is nth clock, so on and so forth everywhere. What I will do here now, the nth clock I will divide into 6, right. So, 6, just a minute. Six sub clocks. There is a clock is around it, another clock around it, another around it, another around it, another. These are the indices. Okay. So, this clock, or you can write this way. So, this clock, the shorter clock, which is, that means clock speed is faster. How many times? 6 times, because period has gone down. So, basically I will employ a 6 times faster clock. Why 6? 6 is coming from the word length, 6 bit word length. From that the figure 6 is coming. I will employ now a 6 times faster clock, and there will be single line through which I will first send in A0n, then A1n, then A2n, then A3n, then A4n, then A5n. So, same period n. So, first this time A0n will go, then this time A1n will go in, here A2n will go in, dot 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 dot. So, I will be using only one line and data will be pushed in at a 6 times faster rate. So, the system will work at a faster clock. But what it will do similarly for B. So, it is called bit serial, it is taking bits serially, not word, the whole word serially, one word after another word, not that. Bits of each word, they are coming serially, not altogether parallelly. A0, A1, A2, A3, A4, A5 for nth parallelly. Okay. Similarly, all right. You can even, for clarity, you can even view it like this, just for interpretation, as though the AN and same for BN, the lines are there. And there is a switch or say commutator, it will first touch this, then this, then this, then this, then this, then this. Okay. So, you have got A0n that will first go in, then A1n, then A2n, all right. So, remember, if this was the time period, this was the nth clock, nth, you will have first one 6n plus 0, the next one will be called 6n plus 1. This is in terms of time, there is a clock around it. I am just marking the indices. 6n plus 0 is the index of the first bit clock under nth word clock. 6n plus 1 is the next, 6n plus 2. So, at 6n plus 0, A0n goes in. If 6n plus 1, A1n goes in. At 6n plus 2, okay. So, actually it is 6n plus 0 and so on, dot 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 6n plus 5, dot 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 dot. Okay, that is what goes in. So, last one is 6n plus 5. All right, very simple. When n is 0, suppose you are starting with the 0th word, That time you have got A0 0, A1 0, A2 0. So, so that time 0th watt clock, it will be divided as 0, 1, 2, 3, 4, 5. Then first it will be what? 6, 7 dot 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 up to 11. So, if you that way go to nth, you will see 6n plus 0, 6n plus 1, 6n plus 2 like that. It is very easy to check. So, you can view as though this data were coming parallelly, but I am using a commutator kind of thing, just running through, I am tapping them one after another at a very faster rate, 6 times faster rate, and whatever coming they are sending you down the line. So, each bit comes down through a very narrow clock pulse, 6 times narrow, or in terms of speed 6 times faster. That is same for A, same for B. But what I am getting here, as I told you, earlier my digital system was doing some processing on A0 and B0, giving the result C0. Parallelly, another processor A1 on B1, giving the result C1, and so on and so forth. So, 6 times I have got the same repetition, or I mean there is an operation which was done 6 parallelly by repeating 6 times. So, hardware and power were going off 6 times, but here every bit clock I will take only one A0, one B0 and do some operation. So, I will not require 6 times hardware will be compressed. So, I will gain power, I will require less power, less hardware, that is the gain, but what I am losing is speed, because I am using 6 times faster clock to run the system, but my original input data rate does not change. 6 times faster because I have made all the bits coming serially one after another, I have to do serial processing. So, I am using 6 times faster clock, but actual input rate or output rate does not go up. Okay. So, it has advantage in terms of power and hardware, 6 times less power, less hardware, but again 6 times more speed. So, loss in speed, gain in power and hardware, this is called bit serial. Given a digit serial system, there is a technique called folding, which we will discuss after some time. You can get bit serial. Given a bit serial, I will show now very soon, you can get back the original digital system, bit parallel or word serial, by unfolding. If I unfold this by a factor 6, all the 6 fellows, 6 data, they will be made as though they are coming out of a buffer, they will be coming parallelly. There will be 6 parallel lines like this for A, 6 parallel lines like B, hardware inside also, if there are some DFG and all that, all nodes will be copied 6 times and original structure will come up. So, from bit serial you can go to word serial by unfolding. Now, there is these two are the opposite ends, extreme ends. One is fully bit parallel, therefore word serial, where you pay in hardware, gain in speed. Another is fully bit serial, okay, where you gain in hardware, because your hardware is less, 6 times less, power is 6 times less, but you lose in speed. Now, there is something in between called digit serial. Your word length, in this case 6, right, A0 to A5, you factorize it, here it is 3 into 2. So, what you can do, you can take 2 bits at a time, A0, A1, let them come parallel. So, not all 6 are parallel, just 2 are parallel, A0, A1 in one clock, in next clock A2, A3 come parallel, and next clock A4, A5. So, I am not taking 6 bit clocks, I am rather taking 3. Okay, what I am saying is, let me draw a diagram and then we will understand. So, 3 into 2, suppose I take 2 lines now, this is for A category, and I take 2 lines, this is for B category. Here I give A0n and A1n. Earlier I had A0, A1, A2, A3 up to A5 parallelly. I say no, A0, A1n, they will be coming together in one cycle, that is called digit cycle. That is, if in the timing diagram, if this is my nth watt cycle, earlier I was dividing into 6 bit clocks. Okay. That is, if you take a factor 6 into 1, 6 bit clocks, now I am taking 3 into 2. So, 3 digit clock, because A0 and A1 together will be called a digit. Earlier A0 it was a bit. Now, together they are coming in 2 bits. Okay, this is called a digit. That is, earlier it was just binary 1 or 0. Now, it is 0 0 or 0 1 or 1 0 1 1. Okay, this is called a digit, and 3 such digits form the full word. So, here the cycle will be divided not in 6 times. So, it will be divided like this, maybe 1, maybe another 1, maybe another 1. So, 0 1 2, that is, it will be 3n plus 0, 3n plus 1, 3n plus 2. Why 3? Because if you start at 0th, you will have 3 cycles, digit cycles, 0th, first, second. During 0th, I send in A0, A1 and B0 n, B1 n. Then during 3n plus 1, I send the next one, A2 n, A3 n, they are parallel. Here also B2 n, B3 n, and during 3n plus 2, A4 n, A5 n, and here B4 n, B5 n. So, in one digit cycle, 2 fellows come here and 2 fellows, 2 bits come, 2 bits come. So, this will have one processor working on A0 and B0, another processor parallelly working on A1, B1. It will give you 2 outputs. So, A0, B0 to be processed by one processor, A1, B1 to be processed by another processor. So, 2 processors are in parallel. Originally, I had 6. By fully digit serial, I could bring it down to 1. So, now I am not bringing it down to 1, I am bringing it down to 2. So, in comparison to digit serial, yes, I will pay more in power, twice in fact, more in hardware. But in comparison to, in comparison to the original one, I am still getting in hardware, because from 6 I have brought down to 2. Similarly, in terms of speed, in the case of digit serial, I was using 6 times faster a clock. It was 0, 1, 2, 3 up to 5. Okay. Now, I am using only 3 times. So, input clock is not going up that much. So, I am not losing that much on speed. I am neither losing too much in power, because instead of I am not neither gaining too much in power, because I am not able to reduce power from 6 times to I am not able to bring down the power by fully 6 times, as I was doing in the case of digit serial, that there are 6 processors parallel, I was bringing down to 1 processor. Now, I am bringing down to only 2. So, I am paying some in power, I am bringing down the power cost just by 3, not by 6. But then at the same time, I am not paying that much. There was gain and here loss. I am not paying that much in terms of speed. Earlier the clock went up by 6, now it is by 3. 1 digit clock, another digit clock, another digit clock. So, during this time, these 2 fellows come together. Sorry, A0, then A2, A3, then A4, A5. Okay. So, start at 0th watt clock, you break it into 3, 0, 1, 2, next fast. So, you break it into 3, 3, 4, 5 and so on and so forth. So, it will be 3n plus 0, 3n plus 1, 3n plus 2. Okay. So, this is something in between. You don't gain fully in terms of power, because you are not bringing down hardware by 6, but only by 3, but don't lose too much in power in speed, because you are not increasing the clock speed by 6, only by 3. Again, from the bit serial you can get back the digit serial just by unfolding, in this case just by factor 2. There I had one bit line only, A0, A1, A2 they are coming together. Now 2 bits will be parallel because unfolded by 2 and you will get this structure. So, if you start with bit serial, you unfold by the entire word length, you get the original digits word serial or bit parallel structure, or you unfold by some intermediate integer. Okay. Like I could have taken 3 bits parallelly, A0, A1, A2, A3, A4, A5. So, 3 bits parallel means 2 cycle, 2 digit cycle per word cycle. Okay. So, 3 processors would have been in parallel. So, I would have paid more in power, but loss in speed would have been lesser, clock would have been just gone up, would have just gone up by 2. Okay. To give an example, consider a 4-bit adder. That is, if you have an adder 4-bit, originally it is A0n, A1n, A2n, A3n, and here you have got what do we do? This is known to all of us who have done a single course on basic digital electronics. You take A0n and take B0n, have a full adder, initial carry is 0, give the result, new carry, then again use the same full adder. So, adders are parallel, new result. Okay. So, this will be C0n, C1n, again use another full adder, this is a carry going in, C2n and one more full adder. So, you see, as I was telling, the processing in this case is adder between A0, B0, same processing is done between A1, B1, same is done between A2, B2 and same is done between A3, B3. So, 4 adders in parallel. So, I am paying 4 times hardware in terms of adder hardware. Okay. This is an example of fully bit parallel or word serial system. Now, I consider fully bit serial. So, that means as an example, I will have nth clock, word clock, it will have 4, okay, 4n plus 0, 4n plus 1, 4n plus 2, 4n plus 3. Okay, this time A0n. So, I will have to use just only one adder, because system will take only one line for A0, only one line for A1, for B. A0, then A1, then A2, A3, similarly B0, then B1, B2, B3, but through only one line. So, at a time only one A bit, one B bit, they have to be added. Suppose this is a full adder, this is one input, I get A0n, then A1n, then A2n, then A3n. LSB comes first. Normally, this is a convention, least significant bit comes first and then other bits. So, first is this at 4n plus 0, then this 4n plus 1, then this at 4n plus 2, then this at 4n plus 3. See, the way they are coming, it is opposite of time axis. This is a convention we follow. This is a leader, it comes first at 4n plus 0, then this the next 4n plus 1, then 4n plus 2, 4n plus 3. Same for this B0n, B1n. Okay, in order to avoid some congestion, here this will be congested. Let me draw B0 from top. Okay. So, initial carry is 0, this is the carry input line. Carry initially is 0. So, there is a switch. Okay. The switch is not FET or MOSFET switch, it is done by mux. This switch will move to here, and when I am adding A0 with B0, that time initial carry is 0. What cycle is it? 4n plus 0. So, at 4n plus 0 for every n, switch will connect here, and here I have got a binary 0, 0 volt stored. And next time at 4n plus 1, whatever be the carry generated in the previous cycle, there is a carry out that will be stored in a flip flop delay, that will come out here, it will switch to that. So, when I go to 4n plus 1, carry generated at 4n plus 0 will come up, and I will move to my switch to this side, 4n plus 1 this side. That time A1 has come, B1n has come, and with that carry generated in the previous cycle stored back and now brought out, that will get added. Okay. So, first C0n will come, again this then C1n, again at 4n plus 1 whatever carry generated, that will be held in the flip flop, at 4n plus 2 that will come here, that time A2n and B2n, with that carry I will get new result, new carry, and like that. So, this is a bit serial structure, okay, working at a 4 times faster clock. But there is a switch here, because it is very tight. I am not giving so much of hardware. Same hardware is used in a time division multiplexed manner. Sometimes it is switching to one side, sometimes it is switching to other side, okay, because hardware is too few. I have to use it for various jobs now. Okay, I have brought down the hardware, that is why switch is required. That is the philosophy, that whenever you do this bit serial thing, or even digit serial thing, you get switches. Now, switches have some problem when you try to unfold them, unfold an edge which has a switch, because switch means discontinuity. Sometimes there is a path is connected, that means path is existing, sometimes path is disconnected, it is not existing. So, how to unfold such a path or edge? That is an issue I will consider next, but let me now consider a digit serial version of this, digit serial with digit size 2. So, in terms of timing diagram, nth will be divided into 2 clocks, 2n plus 0, 2n plus 1. Okay. Like originally 0 1 for 0th input word, then for first input word 2 3 and so on and so forth, 2n 0, 2n plus 1. In 2n plus 0, 2 bits will go in. Okay, 2n plus 0, 2 bits will go in. Philosophically, it will be like this: A0n, A1n will go in, and here B0n, B1n will go in. In the next cycle, next two. So, this is 1 digit, 1 digit. Next cycle A2n, A3n, next cycle, there is a 2n plus 1. At that time B2n, B3n, and 2n plus 1. And output also will be generated like this. In one cycle C0n, C1n, 1 digit. In another cycle C2n, C3n, 1 digit. These are 2n plus 0, these are 2n plus 1. Now, using our engineering common sense, we can design it easily. You understand there will be one full adder between A0 and B0, another between A1 and B1. All right. So, I need 2 full adders. Here we will have A0n added with B0n. Result will come out, this is a full adder, there is a carry input. So, result is coming out, but carry out will then go to the next adder A 1 and B 1. So, here I have got A 1 n and this input carry the full adder, result will be generated. This carry will be stored, because the next cycle when I have got this addition A 2 n B 2 n, that time this carry will be used. So, I put it in a flip flop. There is a switch, initial carry was 0. So, it will move here at 2 n plus 0 cycle. So, it will move here, it will take initial carry as 0, new carry that goes in here, then carry stored, next cycle at 2 n plus 1. This previous carry will be in, that time A 2 n plus B 2 n and that carry will be added, new result. Okay, so, originally I had C 0 n and C 1 n in this cycle 2 n plus 0, next time C 1 n, sorry C 2 n, C 3 n, okay. A 2 n and B 2 n with that carry added, new result, new carry, and this time we will have A 3 n, B 3 n. Okay. This is the digit serial structure. So, from we will show that from our bit serial structure, if we had unfolded it by 2, we would have got this. If we had unfolded by 4, we would have got the original one. This will be a thing we will discuss next time, but then we have to first see how to handle a switch. That is, if there is an edge between two nodes U and V, forget about delay. Earlier, if I had U and V, I had a line directly connecting, means signal is always going from here to here at all clocks. But whenever I switch, it means certain clocks switch is closed and signal is going, at certain other clocks it is open, it is not going. So, it is discontinuous kind of thing, sometimes working, sometimes not. So, how to unfold this kind of structures, that will be the first thing, because you see these switches are coming. This path, for instance, it exists in one cycle, does not exist in another cycle. Okay. This will be the first thing, and then we will use it for this bit serial, digit serial structures. Thank you very much.